Imagine standing above Antarctica, not on the ice itself, but thousands of kilometers above the Earth, looking through the lens of a satellite. Below stretches the largest frozen ocean on our planet. A brilliant white landscape covers millions of square kilometers, reflecting sunlight back into space like an enormous mirror. Everything appears exactly as scientists expect. An endless sheet of sea ice, a continent surrounded by frozen water, a place so cold that winter temperatures routinely fall below -40 degrees Celsius. Then something impossible appears. In the middle of that seemingly unbroken blanket of ice, there is water, dark, open, liquid, hundreds of kilometers from the nearest edge of the sea ice, almost perfectly surrounded by frozen ocean. It looks as though someone has carved a gigantic hole into the Antarctic ice. From space, it resembles an enormous black eye staring back into orbit. This phenomenon has a name. Scientists call it a polynya. At first glance, the word sounds unfamiliar, yet for polar researchers, it represents one of the most fascinating and challenging phenomena in Earth science. A polynya is an area of open water that remains exposed within a region otherwise covered by sea ice. Some are relatively small, others may stretch across tens of thousands of square kilometers. Certain coastal polynyas appear almost every winter, driven by persistent winds, pushing newly formed ice away from the shoreline. These are now reasonably well understood. But there exists another type, far more mysterious, far rarer, and far more difficult to explain. It forms not near the coast, but in the middle of the frozen Southern Ocean. These are known as open ocean polynyas. Unlike coastal openings, they appear hundreds of kilometers away from land. They emerge where thick sea ice should remain continuous throughout the Antarctic winter. Their appearance challenges one of the most basic expectations about polar oceans. Why would liquid seawater suddenly exist in one of the coldest places on Earth? To understand why this question matters, we must first understand Antarctica itself. Contrary to popular belief, Antarctica is not simply a frozen continent. It is the center of one of Earth's most complex climate systems. Surrounding the continent lies the Southern Ocean. Unlike any other ocean on Earth, it flows uninterrupted around the globe. Powerful currents connect the Atlantic, Pacific, and Indian Oceans into a single planetary circulation system. Scientists often describe this circulation as part of Earth's global conveyor belt. It transports heat, it redistributes salt, it moves oxygen into the deep sea, it stores enormous quantities of carbon dioxide. Without this circulation, Earth's climate would look dramatically different. Sea ice plays a crucial role in this system. Every Antarctic winter, seawater freezes across an immense area. As ice forms, it rejects most of its salt. The remaining seawater becomes colder, saltier, and denser. Eventually, this dense water sinks toward the ocean floor, helping drive the deep circulation that influences climates across the globe. In other words, the Antarctic sea ice is not merely frozen water, it is an engine of the Earth's climate. Now imagine that engine suddenly develops an unexpected opening, not along the edges, but directly in its center. Scientists immediately recognized that such openings were not simply visual curiosities. They represented disruptions in one of the planet's most important environmental systems. The story first captured global scientific attention during the winter of 1974. Satellite observations revealed an enormous region of open water within the Weddell Sea. Researchers initially questioned the data. Perhaps the instruments were malfunctioning, perhaps cloud interference had distorted the imagery. Perhaps the apparent opening was merely an observational error, but the hole remained. It continued through multiple observations. Then it appeared again. By 1975, the opening had expanded dramatically. By 1976, it covered an area estimated at more than 250,000 square kilometers, an opening larger than many countries. Then, almost as mysteriously as it had appeared, it vanished. For decades afterward, nothing comparable occurred. The Great Weddell Sea polynya became one of polar science's enduring mysteries. Researchers debated its cause. Oceanographers proposed one explanation. Atmospheric scientists proposed another. Climate modelers struggled to reproduce it inside computer simulations. Some models generated no polynyas at all. Others produced them too frequently. The real Antarctic Ocean appeared to follow rules that scientists had not yet fully understood. Years became decades. Technology improved. Satellites became more sophisticated. Autonomous ocean floats began exploring beneath the ice. Powerful supercomputers transformed climate modeling. Many researchers assumed the mystery had finally been solved. Then, during the Antarctic winters of 2016 and 2017, the ocean surprised everyone. The opening returned. Again, satellites detected an immense region of open water emerging within the sea ice. Although smaller than the famous event of the 1970s, its reappearance stunned the scientific community. The phenomenon was not merely historical, it was still happening. And perhaps it had never truly disappeared. Instead, it had been waiting for the right combination of conditions. Modern observations revealed something equally surprising. The ocean beneath the ice was far more dynamic than previously imagined. Rather than remaining quiet and isolated beneath a frozen lid, deep currents were constantly moving. Layers of warm and cold water interacted. Salt concentrations shifted. Storms transferred enormous amounts of energy into the ocean. The Antarctic winter, once imagined as silent and motionless, was revealed to be astonishingly active. Yet one central question remained unanswered. What initiates the chain of events? What is the first domino? Does the atmosphere begin the process? Do deep ocean currents trigger it from below? Does the salt released during sea ice formation eventually destabilize the entire water column? Or must several rare events occur simultaneously before a polynya can form? Each possibility carries profound implications, because understanding polynyas is not merely about explaining a hole in the ice. It is about understanding how the Earth's climate engine functions. Every answer influences climate models. Every improvement helps scientists predict future sea ice behavior. Every new discovery changes our understanding of how heat moves through the oceans, and ultimately, how our planet responds to a changing climate. But there is another reason why these mysterious openings continue to fascinate researchers. Within these patches of open water, sunlight, heat exchange, ocean circulation, marine ecosystems and atmospheric processes all behave differently from the surrounding frozen sea. A single polynya can influence biology, physics, chemistry, and even weather. It is not simply a hole. It is a natural laboratory, a rare window into processes normally hidden beneath kilometers of ice and months of polar darkness. And despite decades of research, scientists continue to uncover new pieces of the puzzle. The greatest scientific mysteries are rarely mysterious because they are supernatural. They remain mysterious because nature is often more complex than our first explanations. The Antarctic polynya reminds us that even in the age of satellites, artificial intelligence and global observation networks, our own planet can still surprise us. In the next chapter, we descend beneath the frozen surface itself, into the hidden world where invisible currents, ancient water masses, salt, heat, and immense ocean forces interact in complete darkness. Because the true story of the Antarctic polynya does not begin on the ice, it begins thousands of meters below it. At first glance, Antarctica appears motionless. From space, its frozen surface seems silent, stable, and eternal. A vast white shield stretching toward every horizon. But appearances can be deceptive. Beneath that frozen surface lies one of the most dynamic environments on Earth, an invisible world where colossal masses of water are constantly moving, where temperature differences measured in fractions of a degree determine the movement of entire oceans, where salt, an ordinary substance found in every drop of seawater, acts as one of the most powerful forces shaping our planet's climate. To understand why an open ocean polynya forms, we must first leave the world of ice behind. Our journey begins far below the sea surface. Imagine descending through the Antarctic Ocean. The sunlight fades rapidly. Within a few hundred meters, darkness becomes complete. Yet despite the absence of light, this underwater world is anything but still. Enormous currents flow silently across the seafloor. Some originated thousands of kilometers away. Others have remained isolated from the atmosphere for centuries. These water masses differ in temperature, salinity, and density. Together they form a layered ocean, much like a giant invisible cake, with each layer resting upon another. Normally, these layers remain remarkably stable. The coldest and freshest water occupies the surface beneath the sea ice. Below it lies warmer, saltier water. This arrangement may seem unusual. After all, warm water is expected to rise. But in the ocean, temperature is only part of the story. Salt changes everything. Saltier water becomes denser. Even when it is slightly warmer, it can remain trapped beneath colder, fresher water. This delicate balance creates a natural barrier. Oceanographers refer to it as stratification. Stratification prevents heat stored in deeper waters from easily reaching the frozen surface. For much of the Antarctic winter, this invisible barrier protects the sea ice from melting below, at least most of the time. The Southern Ocean is unique among Earth's oceans. Powerful winds circle Antarctica almost continuously. Driven by the planet's rotation and enormous atmospheric pressure differences, these winds generate the Antarctic circumpolar current, the strongest ocean current on Earth. Unlike currents in other oceans, it flows completely around the continent without interruption. Every second, this immense current transports more water than all of Earth's rivers combined. Its energy penetrates deep into the ocean. It shapes global circulation. It influences climate across every continent. Yet beneath this powerful circulation lies another remarkable feature. Hidden hundreds of meters below the surface is a relatively warm body of water known as circumpolar deep water. The word warm is relative. Its temperature is only a few degrees above freezing. But in Antarctica, a difference of even 1 or 2 degrees Celsius can determine whether ice survives or disappears. This deep water carries heat accumulated from oceans across the globe. Normally, stratification prevents it from reaching the surface, but nature is rarely static. Throughout the Antarctic winter, sea ice continues to grow. As seawater freezes, something extraordinary happens. The ice crystals themselves contain very little salt. Instead, salt is expelled back into the surrounding ocean. This process is called brine rejection. The surrounding seawater becomes increasingly salty, and because salt increases density, the water grows heavier. Eventually, this dense water begins to sink. As it descends, it pulls surrounding water downward with it. This motion is known as deep convection. Under ordinary conditions, convection remains relatively limited, but if enough dense water forms, the process can intensify dramatically. Imagine removing the stopper from a bathtub. Water rushes downward, new water flows in to replace it. In the Southern Ocean, something similar can occur on an enormous scale. As surface water sinks, deeper water rises to replace it. That replacement water carries heat. Not tropical heat, not even temperate heat, but heat sufficient to weaken sea ice from below. For decades, scientists believed this mechanism might explain the mysterious Weddell Sea polynya. The idea seemed elegant. Growing sea ice creates dense salty water. Dense water sinks. Warmer deep water rises. The upward heat melts ice. An opening appears. Simple, logical. Yet observations revealed a more complicated reality. The ocean did not always behave according to this sequence. Sometimes dense water formed without producing a polynya. Sometimes warm water approached the surface without melting enough ice. Clearly, another ingredient was missing. That missing ingredient appeared to come from above: winter storms. The Southern Ocean experiences some of the most intense storms on Earth. Cyclonic systems sweep around Antarctica with extraordinary force. Their winds generate massive waves. Even beneath expanding sea ice, these storms transfer mechanical energy into the ocean. Rather than leaving the water undisturbed, powerful winds stir the upper ocean like a giant invisible spoon. Ocean layers begin mixing. The protective stratification weakens. Heat from below moves upward more easily. Several recent studies suggest that particularly strong storms may play a crucial role in initiating open ocean polynyas. The timing is striking. Satellite observations from 2016 and 2017 coincided with unusually intense atmospheric conditions over the Weddell Sea. Researchers proposed that these storms disrupted the stable layering enough for deep, warm water to begin rising. Once the process started, it reinforced itself. More warm water melted more ice. More open water allowed greater heat exchange with the atmosphere. More convection developed. The system entered a powerful feedback loop, yet even this explanation remained incomplete, because another actor was quietly influencing events from below. The sea floor itself. The bottom of the Weddell Sea is far from flat. Ancient underwater mountains, ridges, basins, and steep continental slopes shape the movement of deep currents. These geological features guide water like invisible highways. Some force deep water upward, others trap dense water within enormous underwater valleys. Researchers using autonomous underwater instruments discovered that relatively small changes in current direction around these submarine ridges could dramatically alter how much heat reached the surface. In other words, the shape of the ocean floor influences whether a hole may eventually appear in the ice above. This realization transformed scientific thinking. A polynya is not caused by a single process. It is the product of an intricate partnership: atmospheric circulation, ocean currents, sea ice formation, salt rejection, deep convection, submarine topography, and climate variability. Each contributes a piece. None acts alone. It is much like an orchestra. One instrument cannot perform a symphony by itself. Only when every section plays together does the full performance emerge. The Antarctic Ocean behaves in much the same way. One storm is insufficient, one warm current is insufficient, one patch of salty water is insufficient. But when multiple conditions align, nature produces one of the rarest events ever observed in Earth's polar oceans. Perhaps the most remarkable discovery of recent decades is not that scientists have solved the mystery. It is that they have learned how astonishingly interconnected the Earth's systems truly are. The atmosphere influences the ocean reshapes the ice alters the atmosphere. Each process feeds the next in an endless cycle, a change measured in fractions of a degree. A slight shift in wind direction, a subtle increase in ocean salinity. Together, they can create an opening visible from space, an opening large enough to transform an entire region of the Southern Ocean. But an even deeper question remains. If these processes have always existed, why do giant open ocean polynyas appear so rarely? Why did the Great Weddell Sea opening disappear for decades before returning? What hidden threshold determines whether the ocean remains frozen or suddenly opens? To answer that question, scientists had to gather evidence from one of the most inaccessible places on Earth. Not from satellites, not from ships, but from robotic explorers drifting silently beneath kilometers of Antarctic ice, collecting measurements where no human diver could ever reach. What those instruments discovered would reshape our understanding of the frozen continent and reveal that Antarctica is far more sensitive to change than anyone had imagined. For decades, one simple question continued to puzzle scientists. What actually happens beneath the Antarctic sea ice before a giant polynya appears? Satellites could see the surface. They could measure the size of the opening. They could monitor sea ice expanding and shrinking across the Southern Ocean. But satellites could not see through hundreds of meters of seawater. The most important events were taking place far below the ice. In complete darkness, beyond the reach of ships, beyond the reach of divers. For much of the 20th century, this hidden world remained almost impossible to observe. Researchers relied on occasional expeditions during the short Antarctic summer. Ships collected water samples. Scientists lowered instruments into the ocean. Measurements were taken. Then the ships departed. The Antarctic winter arrived. Sea ice spread across the ocean, and the most critical months became completely inaccessible. Ironically, scientists could only study the ocean during the season when the mysterious polynyas usually did not form. The events they most wanted to observe occurred during the long polar winter, when no research vessel could safely reach the area. It was like trying to understand a volcanic eruption by visiting the volcano only after the eruption had ended. The missing evidence remained hidden beneath the ice. Everything began to change in the early 21st century. Oceanographers developed a new generation of autonomous scientific instruments capable of surviving one of the harshest environments on Earth. Among the most important were robotic ocean floats known as Argo floats, including a specialized version designed for polar regions. Unlike research ships, these robots could remain in the ocean for years. Unlike satellites, they could travel beneath the ice. Each float drifted silently with the ocean currents. Every several days it descended to depths of nearly 2,000 meters before slowly rising back toward the surface. Along the way, it measured temperature, salinity, pressure, and increasingly dissolved oxygen, carbon content, and other chemical properties of seawater. Whenever open water became available, the float transmitted its observations to satellites before diving once again into the darkness. These robotic explorers transformed polar science. For the first time, researchers could monitor the Antarctic Ocean continuously throughout the year, not just during summer expeditions, not just from space, but from inside the ocean itself. Then came the winter of 2016. As satellites detected the unexpected return of the Weddell Sea polynya, something extraordinary happened. Several autonomous floats were already drifting beneath the surrounding ice. Without anyone controlling them in real time, they happened to be in exactly the right place. For polar scientists, it was an extraordinary stroke of fortune. The robots recorded conditions before the opening formed. They remained nearby as it expanded, and they continued collecting data after it disappeared. For the first time in history, researchers possessed direct measurements from inside an active open ocean polynya. The data revealed something remarkable. Long before the sea ice broke apart, warmer deep water had already begun moving upward. Not suddenly, not violently, but gradually. The ocean's layered structure was weakening. The protective barrier separating cold surface water from warmer deep water was beginning to collapse. As deep water rose, it carried heat toward the underside of the sea ice. That heat alone was not enough to melt enormous areas of ice, but it started a chain reaction. The rising water also brought additional salt toward the surface. The surface ocean became denser. Denser water sank more easily. As it descended, even more warm water rose from below. The cycle strengthened itself. Scientists call this process positive feedback. Each stage reinforced the next. Warm water weakened the ice. Open water allowed greater heat exchange between the ocean and atmosphere. Enhanced cooling at the surface created even denser water. That dense water sank faster, which pulled even more warm water upward. Once the cycle reached a critical threshold, the opening expanded rapidly. What appeared from space as a sudden event had actually been developing beneath the surface for weeks, perhaps even months. The ocean had been preparing the conditions long before anyone noticed the first patch of open water. The robotic observations confirmed another important discovery. The Southern Ocean stores enormous amounts of heat below the surface. Although these waters remain cold by everyday standards, they contain enough energy to influence sea ice over vast regions. This finding surprised many climate researchers. It demonstrated that Antarctica's frozen appearance can hide a remarkably dynamic ocean beneath. Yet the robots also revealed something equally important. Heat alone does not create a polynya. Many regions contain relatively warm deep water without developing large openings in the sea ice. Instead, multiple conditions must occur simultaneously. Ocean stratification must weaken, deep convection must begin, atmospheric storms must transfer energy into the upper ocean. Ocean currents must transport warm water toward the correct location. Even the underwater landscape influences the movement of those currents. Only when all these processes align can a giant open ocean polynya emerge. This explained why such events are so rare. The Antarctic Ocean is constantly balancing between stability and instability. Most winters, the balance remains intact. Occasionally, nature reaches a tipping point, and the frozen ocean briefly opens. The robotic measurements also improved climate models. For decades, many computer simulations struggled to reproduce the formation of open ocean polynyas. Some predicted far too many, others predicted none at all. The new observations provided real-world data that allowed scientists to refine their models. As those models improved, researchers gained a better understanding of how the Southern Ocean transports heat, carbon, and oxygen around the globe. The implications extended far beyond Antarctica. The Southern Ocean absorbs roughly 40% of the excess heat entering Earth's oceans due to global warming. It also absorbs a substantial portion of the carbon dioxide produced by human activities. Understanding how this ocean functions is essential for predicting future climate change. A single polynya may seem like an isolated event. In reality, it influences global ocean circulation. It affects marine ecosystems. It alters the exchange of gases between the ocean and atmosphere. And it may influence how efficiently the Earth stores heat beneath the sea. The mystery was no longer simply about a hole in the ice. It had become part of a much larger story. A story about the climate system of an entire planet. Yet despite these remarkable discoveries, one profound question remained unanswered. Were the recent polynyas simply rare natural events? Or were they becoming more likely in a warming world? Could climate change alter the delicate balance that has controlled the Antarctic Ocean for thousands of years? Scientists remain cautious. Current evidence suggests that no single cause can fully explain every polynya. Natural climate variability continues to play a major role. At the same time, rising ocean temperatures, changing wind patterns, and shifts in sea ice may influence how often these extraordinary openings occur in the future. The challenge is that Antarctica changes slowly. Some processes unfold over decades, others over centuries. Understanding them requires patience, continuous observation, and increasingly sophisticated technology. Every new expedition adds another piece to the puzzle. Every autonomous robot sends back another chapter in the story, and every winter reminds scientists that the Southern Ocean still holds many secrets beneath its frozen surface. In the next chapter, we move beyond the science of how polynyas form and confront an even larger question. What do these mysterious openings mean for the future of Earth's climate? Could they become more common as the planet warms? Or are they simply one of nature's rarest but entirely natural phenomena? The answer lies at the intersection of climate science, oceanography, and one of the most important environmental challenges humanity has ever faced. Every scientific discovery eventually leads to a larger question. Not simply what is happening, but what does it mean? For decades, open ocean polynyas were regarded primarily as fascinating polar phenomena. Rare events, scientific curiosities, unexpected openings in an otherwise frozen sea. Today, they are viewed very differently. Modern climate research has revealed that these openings are not isolated events. They are connected to some of the most important processes regulating Earth's climate. To understand why, we must look beyond Antarctica itself. The Southern Ocean is often called the heart of the global ocean. Unlike any other body of water, it connects the Atlantic, Pacific, and Indian Oceans into a single continuous circulation system. Oceanographers sometimes describe this system as the planet's great conveyor belt. Heat moves through it, carbon moves through it, oxygen moves through it. Nutrients move through it. The circulation of the Southern Ocean influences marine ecosystems across the globe. It also affects weather and climate far beyond Antarctica. When an open ocean polynya forms, this circulation changes. The opening exposes seawater directly to the cold Antarctic atmosphere. Enormous quantities of heat escape into the air. At the same time, the ocean exchanges gases with the atmosphere more efficiently than when covered by ice. Carbon dioxide enters the water, oxygen dissolves into the ocean. Water becomes colder and denser, Some of that dense water sinks toward the deep ocean, helping drive the global overturning circulation. This process may sound technical, but it has enormous consequences. The deep ocean acts as one of Earth's greatest reservoirs of heat. It also stores vast amounts of carbon dioxide that would otherwise remain in the atmosphere. In many ways, the ocean slows the pace of climate change. Without this natural storage system, global temperatures would already be significantly higher. That is why scientists pay such close attention to changes in the Southern Ocean. Even relatively small alterations in Antarctic ocean circulation can influence climate on a planetary scale. The question, however, is whether climate change itself could alter the conditions that produce polynyas. The answer is more complicated than many people expect. It would seem logical to assume that a warmer world should simply melt more ice and produce more openings. But Antarctica rarely behaves so simply. Several competing processes occur simultaneously. As the atmosphere warms, some regions of Antarctica experience increased melting from glaciers and ice shelves. This introduces more fresh water into the surrounding ocean. Fresh water is less dense than salty seawater. As more fresh water accumulates near the surface, stratification becomes stronger. A stronger stratified ocean makes it more difficult for warm, deep water to rise. In theory, this could reduce the formation of some open ocean polynyas. At the same time, another process pushes in the opposite direction. Climate change is also altering wind patterns over the Southern Ocean. Several studies suggest that stronger or differently positioned storms can increase ocean mixing. More mixing weakens stratification. Weaker stratification allows warm, deep water to move upward more easily. That process favors polynya formation. Meanwhile, the deep ocean itself continues storing excess heat generated by global warming. The Southern Ocean has absorbed an extraordinary amount of this additional energy over recent decades. Much of that heat remains hidden beneath the surface. Invisible to satellites, invisible to human observation, yet still capable of influencing Antarctic sea ice under the right conditions. Scientists therefore face a complex challenge. Some climate processes make giant polynyas less likely. Others make them more likely. The balance between these competing forces remains one of the most active areas of polar research today. This uncertainty is not a weakness of science. It is an honest reflection of the complexity of Earth's climate system. Science advances by measuring uncertainty, not by pretending certainty exists where it does not. One lesson has become increasingly clear: the Antarctic Ocean is far more sensitive than researchers once believed. Small changes in temperature, small changes in salinity, small shifts in wind patterns. Together they can alter the stability of an ocean covering millions of square kilometers. This sensitivity extends beyond sea ice. Marine ecosystems also respond rapidly to the appearance of a polynya. When sunlight returns during the Antarctic spring, open water receives far more light than ice-covered regions. Microscopic algae, known as phytoplankton, begin growing rapidly. These tiny organisms form the foundation of the Antarctic food web. Krill feed on phytoplankton. Fish feed on krill. Penguins, seals, whales, and seabirds depend directly or indirectly upon this chain of life. In some years, a polynya becomes an oasis of biological productivity surrounded by frozen ocean. Researchers have documented unusually high concentrations of marine life near recurring coastal polynyas. Even temporary open ocean polynyas may provide feeding opportunities for wildlife capable of reaching them. Yet there are risks as well. If sea ice patterns change dramatically over long periods, species that depend on stable seasonal ice may struggle to adapt. Many Antarctic organisms evolved over millions of years within remarkably predictable environmental conditions. Rapid changes challenge that stability. Understanding these ecological responses remains another important frontier of scientific research. Meanwhile, climate models continue improving. Supercomputers now simulate interactions between the atmosphere, sea ice, ocean currents, and marine ecosystems with unprecedented detail. Artificial intelligence is beginning to help researchers identify subtle patterns hidden within enormous climate datasets. Autonomous underwater robots continue collecting observations beneath Antarctic ice throughout the year. Satellites monitor sea ice with increasing precision. Each technological advance provides another piece of the puzzle. And yet, despite all these innovations, Antarctica continues to surprise us. Nature often reminds us that observation and prediction are not the same. Scientists may understand individual physical processes very well. Predicting exactly when all of those processes will align remains extraordinarily difficult. That is why the return of the Weddell Sea polynya in 2016 captured worldwide attention. It demonstrated that even phenomena absent for decades can reappear when conditions become favorable. Not because nature has broken its rules, but because those rules are more intricate than we once imagined. Perhaps that is the greatest lesson of all. The Antarctic Ocean is neither fragile nor invincible. It is dynamic. It responds continuously to countless interacting forces, some natural, some increasingly influenced by human activity. The challenge facing scientists is not simply to explain what happened in the past. It is to understand what may happen next. Because the frozen waters surrounding Antarctica do far more than shape one remote continent. They help regulate the climate of an entire planet. In the final chapter, we bring together decades of scientific discovery to answer the central question that began this journey. Is the Antarctic polynya truly a mystery? Or has science finally uncovered the hidden mechanism behind one of Earth's most extraordinary natural phenomena? And perhaps more importantly, what does this remarkable story teach us about our own planet and our place within it? We began this journey with what seemed like an impossible sight. A vast hole of open water appearing in the middle of one of the coldest and most remote oceans on Earth. From space, it looked almost unnatural. A dark opening surrounded by an endless landscape of ice. For decades, it inspired curiosity, debate, and countless scientific investigations. Some wondered whether it was an error in the satellite images. Others questioned whether such an event should even be possible. Today, after decades of research, we know that the phenomenon is very real. It has been observed repeatedly by satellites. It has been measured by research expeditions. It has been monitored by autonomous underwater robots drifting beneath the Antarctic ice. And it has become one of the most valuable natural laboratories for understanding how our planet works. The Antarctic polynya is not a crack in the continent. It is not evidence of a hidden civilization. It is not a gateway beneath the ice, nor is it proof of any extraordinary or supernatural phenomenon. Instead, it is something far more remarkable. It is a demonstration of the extraordinary complexity of Earth's natural systems. Its formation depends on an intricate balance between ocean circulation, sea ice, atmospheric storms, underwater topography, temperature, and salinity. No single force creates a polynya. Rather, it emerges only when many independent processes align in just the right way. like the pieces of an enormous puzzle finally fitting together. Throughout this documentary, we have followed that puzzle piece by piece. We explored the frozen landscape visible from space. We descended into the hidden world beneath the sea ice. We followed robotic explorers into waters no human could directly observe during the Antarctic winter. And we discovered how tiny differences in temperature and salt can influence an ocean spanning millions of square kilometers. Perhaps the most surprising lesson is that Antarctica is far from silent. Although it appears frozen and motionless, it is constantly changing. Powerful currents flow beneath its ice, storms reshape its surface, dense water sinks toward the deepest parts of the ocean. Heat stored thousands of meters below slowly moves through invisible pathways. Even during the long polar night when darkness covers the continent for months, the Antarctic Ocean remains alive with motion. Every winter, countless physical processes interact continuously. Most of the time, they remain in balance. Occasionally, that balance shifts, and a giant opening appears in the sea ice. What once seemed mysterious becomes understandable, not because nature has become simpler, but because science has gradually revealed more of its hidden mechanisms. Yet one important truth remains. Science has not answered every question. Researchers continue studying why some winters produce large open ocean polynyas while others do not. They continue refining climate models. They continue deploying autonomous robots beneath the Antarctic ice. They continue improving satellite observations. Each expedition uncovers new information. Each year adds another chapter to the story. This is the true nature of scientific discovery. Science is not a collection of permanent answers. It is a process of continuous investigation. Every discovery reveals new questions. Every solution exposes deeper layers of complexity. The Antarctic polynya reminds us that uncertainty is not failure. It is the frontier of knowledge, the place where future discoveries begin. Its importance extends far beyond Antarctica. Understanding these rare openings helps scientists improve predictions of global ocean circulation. It strengthens climate models used to forecast future environmental change. It improves our understanding of how heat and carbon move through Earth's oceans. It helps explain how marine ecosystems respond to changing conditions, and ultimately, it provides valuable insight into the stability of Earth's climate system itself. The story of the Antarctic polynya is therefore not only about a remote region of ice. It is about the entire planet. Every continent is connected through the oceans. Every ocean is connected through circulation. Every circulation influences climate, and climate influences every living organism on Earth. The frozen waters surrounding Antarctica may appear distant from our daily lives, yet they quietly help regulate the world we all share. Perhaps that is the greatest revelation of all. The most extraordinary mysteries are often not hidden because they are impossible to explain. They remain hidden because they occur in places few people can reach, through processes too vast for human eyes to observe directly. Only through decades of careful measurement, international cooperation, technological innovation, and scientific curiosity have we begun to understand what was once invisible. The Antarctic polynya teaches us something profoundly important. Our planet is not a static world. It is a living system of interconnected oceans, atmosphere, ice, land, and life. Every component influences the others. Every change echoes through the system. The better we understand these connections, the better prepared we are to protect the future of our world. Even now, somewhere above Antarctica, satellites continue their silent orbit. far below them, autonomous robots drift through the dark waters beneath the ice. Research stations remain vigilant through months of isolation and extreme cold. Scientists around the world analyze new streams of data every single day. The story is still unfolding. New discoveries will come, new questions will emerge, and the Southern Ocean will continue to challenge our understanding, just as it has for generations. Because nature always has another lesson waiting for those willing to observe carefully. And perhaps that is the greatest mystery of all. Not that Antarctica still holds secrets, but that, even in the 21st century, our own planet remains capable of surprising us. Thank you for joining this scientific journey into one of Earth's most fascinating natural phenomena. The mystery of the Antarctic polynya is no longer simply the story of a hole in the ice. It is the story of a planet in constant motion, a reminder that every discovery deepens our appreciation of the remarkable world we call home.